Since a black hole is a sphere, why do we call it a black hole instead of a black ball? You could say it's because anything that falls into it can never come back out. So it's like a bottomless hole. But where do things that fall into a black hole actually go? Do they eventually enter the interior of the black hole? Or do they remain frozen forever on its world sheet? To answer this question, you may first need to clarify another one. What does the inside of a black hole actually look like? A black hole has two strange features. One is the gravitational singularity, and the other is its event horizon. Early on, scientists discovered that, both at the center of a black hole and at the Schwarzschild radius, the Schwarzschild solution diverges. In other words, it runs into infinities. In principle, infinities should exist only in mathematics. In the real physical world, true infinities are generally believed not to exist. When dealing with any physical problem, if an infinity appears in your calculations, it usually means that something has gone wrong in your derivation. As a result, the Schwarzschild solution at the time mainly described regions outside the black hole's world sheet. As for what lies inside a black hole, we knew nothing at all. However, infinities are not always unsolvable. Sometimes, mathematical techniques can be used to eliminate them, such as renormalization or changing the coordinate system. Later on, when people transformed from Schwarzschild coordinates to Kruskal coordinates, the divergence at the event horizon was resolved. At that point, humanity finally gained a basic understanding of the structure of black holes. For stars with sufficiently large mass, once their internal fuel is exhausted, the collapse of the entire star toward the center becomes continuous. What does continuous mean? It means that no matter what, whether electron degeneracy pressure or neutron degeneracy pressure, nothing can stop it. At this stage, no known force can prevent the collapse from happening. This collapse continues endlessly, until all matter is compressed into a single point. This point is the gravitational singularity at the center of a black hole. Therefore, from the perspective of classical general relativity, aside from that central point, everything inside a black hole is vacuum. Although this explanation aligns with mainstream theory, it is almost certainly incorrect. Why? Because even though the event horizon problem was resolved, the singularity problem was not. The core of general relativity is smooth, continuous spacetime. Within this framework, the origin of a black hole has no size, its volume is zero. That leads directly to an infinite density. While a coordinate transformation can eliminate the divergence at the event horizon, the divergence at the singularity has never been resolved within general relativity. This is one of the reasons physicists believe general relativity is incomplete. So what can be done? When in doubt, turn to quantum mechanics. If gravity alone can't solve the problem, then try adding some quantum theory. In 2001, scientists extended concepts from condensed matter physics to gravitational systems, and derived a special kind of celestial object from Einstein's field equations. It is a spherical object extremely similar to a black hole, but unlike a black hole, it has neither a singularity nor an event horizon. Instead, it contains a special vacuum wrapped in a thin shell. This vacuum is not vacuum in the traditional sense. It is a vacuum known as de Sitter space, which has extremely high energy, and tends to expand in all directions. However, this intense expansion is ultimately confined by a layer of matter thinner than an atomic nucleus, yet extraordinarily dense. The material in this shell comes from the final remnants of massive stars, the very matter that would otherwise have collapsed into a black hole. The authors called this hollow object, which is neither a black hole nor a neutron star nor a quark star, a gravastar, also known as a gravitational vacuum star. From the moment it was proposed, the gravastar was regarded as an alternative model to black holes. By introducing quantum theory, it not only resolves the problems of singularities and event horizons, but even eliminates the black hole information paradox. So how does a gravastar form? In fact, the process is similar to that of a black hole. When a massive star reaches the end of its evolution, its matter begins to collapse uncontrollably toward the center. But unlike black hole theory, the matter does not compress inward without limit. Instead, once compression reaches a certain point, it triggers a phase transition in the central vacuum, transforming it into a de Sitter vacuum. Once a de Sitter vacuum forms at the center, it behaves like a bubble and rapidly expands due to enormous pressure. As the bubble grows, it pushes the surrounding stellar remnant material outward. On one side, gravitational collapse continuously squeezes matter inward. On the other, the de Sitter vacuum forcefully pushes matter outward. Eventually, the matter reaches a force balance near the Schwarzschild radius, and becomes an ultra-high-density spherical shell. This shell, together with the vacuum it encloses, is the gravastar. It can be seen that gravastars and black holes share many similarities. For example, their sizes are comparable. The shell lies essentially near the Schwarzschild radius, which is effectively equivalent to a black hole's event horizon. Secondly, the shell's external behavior closely resembles that of a black hole. It is composed of stellar mass material, possesses enormous gravity, and can produce gravitational lensing effects just like a black hole. At the same time, its extreme gravity causes severe gravitational redshift. That is, as photons move through a gravitational field, their wavelengths are stretched in order to escape the gravitational potential, and their frequencies decrease. As a result, the closer an object is to the shell, the redder and dimmer its light becomes, very similar to what happens near a black hole's event horizon. However, because the shell has a finite thickness, it does not possess the infinite redshift surface characteristic of black holes. In addition, its gravity is strong enough to produce observational features similar to a black hole shadow, making gravastars appear just as dark as black holes. Their surface temperatures are close to absolute zero, and they cannot be directly detected through thermal radiation. Another similarity to black holes, the difference is that their temperature distribution may not be as uniform as that of a black hole's surface. Beyond that, gravastars, like black holes, also attract external matter and form accretion disks. But the difference is that, for gravastars, this matter is ultimately compressed onto the shell and becomes part of it. For black holes, however, this matter eventually crosses the event horizon and enters the interior, heading toward the singularity. But the act of crossing the horizon and reaching the singularity is described from the reference frame of the infalling matter itself. From an external reference frame, we only observe the matter growing dimmer and slower as it approaches the black hole, eventually appearing to freeze at the event horizon, a behavior similar to that of a gravastar. One crosses the horizon, the other appears to stop at the horizon. Why does the same event seem to produce two contradictory outcomes? In fact, there is no contradiction. Setting aside the mathematical formalism of general relativity, you can understand it this way. When you see an object frozen at the event horizon, it's because the light it emits takes an infinite amount of time to reach the outside world. But in reality, the object has already entered the black hole. It's just that no information from that point onward can ever escape. This is precisely the meaning of the term event horizon, the visual boundary of events. Once something crosses that boundary, you can never see it again. Its future has nothing to do with yours. From this perspective, the greatest difference between black holes and other celestial objects is that a black hole is a special structure of spacetime itself, rather than a traditional object made of matter. For this reason alone, a gravastar, an ordinary object composed of matter, is obviously easier for the public to accept. Given all the advantages of the gravastar model, what is the cost? Although everything outside the shell is easier to explain, the shell itself, and the special vacuum inside it, become new problems. By comparison, black holes are extraordinarily simple. After all, black holes have no hair. Aside from mass, angular momentum, and electric charge, a black hole has no other physical properties. There is no need to care about the form of matter that created it. Gravastars are different. Although the shell that composes them is exotic, it is still matter. And if it is matter, it must have internal structure and an equation of state. At present, these are still not well understood. Furthermore, what exactly is the de Sitter vacuum inside the shell? These are all questions that remain to be clarified in the future. At present, gravastars are only a rough theoretical model. To accurately describe their physical properties, a complete theory of quantum gravity is indispensable. However, beyond pure theory, scientists are also trying to find observational evidence, either to support or refute the idea. That is, they are looking to see whether the black holes we observe in reality might actually resemble gravastars more closely. Although the two behave extremely similarly, their fundamentally different natures mean that subtle differences should still exist. For example, when two such objects collide, the gravitational wave signals during the early stages of merger would not be exactly the same. Therefore, in the future, gravitational wave detectors with higher precision may finally be able to decide between these two models.